Okay, so maybe we can start the lecture. Okay, so as I said, last time we did some results which had to do with quantum field theory and curved spacetime. And some of you might even have wondered, what these results, which, as was pointed out, hold in any state in any quantum field theory and curved spacetime, have to do with black holes. So in today's lecture and in tomorrow's lecture, we are going to show how these very simple results actually are surprisingly powerful, and how this fact that we derived about the short distance physics of correlation functions across the black hole horizon is actually powerful enough to let us derive the form of Hawking radiation when you combine it with some simple properties of the black hole geometry. So what I'd like to do first is just review some simple aspects of the kind of black hole geometry. And I wanted to actually start by discussing black holes in flat space. And then we will discuss black holes in ADS as well. But it's nice to start by discussing flat space. So of course, when we say flat space, I mean asymptotically flat space. The space-time is a black hole space-time. But what this means is that if you go very far away, very far away from where the matter was, then the metric starts looking like Minkowski space. And there's a simple Penrose diagram that describes the kind of process we are looking at. And that Penrose diagram is the usual Penrose diagram that you've seen drawn, where you have some horizon. Oops. Where you have a horizon here. You have some singularity here. And the black hole is a black hole which is formed from the collapse of matter. So it's important that, at most parts in this course, because we want to talk about the information paradox, we are not considering what are sometimes called eternal black hole spacetimes, but we are going to consider black holes that are formed from collapse. And what that means is that, there's some infalling matter, which is all this region. And so there's some matter, and this is the world line of the matter, the thing that I shaded in brown. And this matter is what actually formed, caused the black hole to form. And as I already discussed, this is just the origin of polar coordinates. Okay. Now, what we want to do is not analyze this entire space-time. In fact, one can write down, if one makes some simple assumptions about what the form of the infalling matter is, if one thinks of some spherically symmetric dust configuration, one can in fact write down the entire metric for this process that I have shown on the blackboard. This is sometimes called the Openheimer Schneider metric. In fact, there's an interesting historical story here. This metric was studied a couple of years before Oppenheimer and Schneider by a Bengali physicist called B. Dutt, whose work is actually virtually unknown. And in fact, actually, it turns out this person B. Dutt, very little is known about him personally, because he, in fact, himself died a couple of years after writing this paper. And so, when historians at some point tried to even trace who this person was, I think they couldn't even find out much about this person. At least I don't know much about the person. But there is a paper that you can find that is a couple of years before this Oppenheimer-Schneider paper that does study this metric or these kinds of collapsing geometries. But the point is, in any case, if you take some dust and you write down some kind of stress energy tensor for the matter, you can find the entire metric. But our interest in this course is almost never going to be in this entire process of collapse. Okay, so our interest is actually going to be in a different region. It's going to be in some region that's here. Okay? I hope you can see the red mark here. So it's going to be in some region that is well away from the singularity. Okay, it is also well away from the infalling matter, and it's somewhere in the vicinity of the horizon. Okay, so this is an important point. So we don't want to study the singularity, which is here. We don't want to study the singularity, which is here. Okay? We don't want to study the singularity because we don't know what happens at the singularity, and maybe strong quantum gravity effects become important. We could study the infalling matter by putting in some assumptions about what the infalling matter is. So we could study the metric in this part. But in fact, the nice part about framing the information paradox and everything that we are going to do, and also the form of Hawking radiation, is that we don't need to make reference to the details of the infalling matter. Okay? So we are considering some region here which is at late times, and it's far away from both the infalling matter and from the singularity. Okay, so in this limit, in this late time limit, it turns out that the metric becomes very simple, and one can explicitly write down what the metric is. So I'm going to write t goes to infinity, but I'll explain in a minute what we mean precisely by t goes to infinity. The metric becomes very simple. It's some generalization of the Schwarzschild metric. The reason I say generalization is because we are happy to study this process in d+1 dimensions. And in d+1 dimensions, this function f of r, this is just the Schwarzschild solution in d+1 dimensions, is 1 minus mu by r to the d minus 2. Okay, so notice that, instead of having 1 minus mu by r, we have 1 by mu to the r to the d minus 2. We are always in d+1 dimensions of our usual 4-dimensional spacetime. D is equal to 3, and this becomes the familiar 1 minus mu by r metric. This mu is not quite the mass, it's a mass parameter, and I'll write down for once what the relationship between this mu and the mass of the black hole is, but this relationship will not be important, so we'll keep coming across this function f of r, but this relationship will not be important, but I'll write it down for once. And the relationship is just given by some constants, which one can work out.
It's 2m by r, right?
No, I haven't said right now what the mass is. 1 second, please.
Okay.
Yeah. Okay. So this is the mass. Okay. There's also a factor of g Newton. So that's the point I was trying to make, was that this mu is some mass parameter, and it's related to the actual mass of the black hole by this factor, which involves a factor of g Newton and various other dimension dependent terms. And you can check that in d equals 3, this in fact does indeed turn out to be just twice m over r. In other higher dimensions, there's some other more complicated relationship between this mu and this and the mass, which is this capital M, but we are not going to need this relationship. So for us, we are happy to work with this mass parameter, which is related by some dimension dependent constant to the mass. Okay? Now the horizon is obviously at RH equal to mu to the 1 by d minus 2. Okay, and at the horizon is the point where f of RH equal to 0. Okay? So this is just some very basic facts about the geometry. Now, perhaps the most interesting thing in what I wrote, I'm guessing that this geometry, or at least in 4 dimensions, is familiar to many of you. But there's an interesting thing I wrote here, which is t goes to infinity, okay? Which is, I hope you can see the laser pointer, and it says t goes to infinity. Now, what does one mean by t goes to infinity? So this is something which is important. It's an important physical point. So t goes to infinity means, okay, that t is much greater than RH after collapse. Okay, so there's a horizon radius, and if you set times in terms of that horizon radius or in terms of the light crossing time of that horizon radius, we want this time that we are exploring this metric at to be much greater than the light crossing time of the horizon radius. The reason for that is that we expect that in this kind of a time, the perturbations, whatever classical geometry remnants of the infalling matter remain, will all die down, and the metric will indeed become the metric that I wrote. And so that's important. But it's also important that, when I draw this kind of a Penrose diagram, so this Penrose diagram that I drew, which I can copy here for our reference. In this Penrose diagram, let me just paste it here. We are not, this Penrose diagram is not a valid Penrose diagram if you start considering times that are so late that the black hole has started evaporating. Okay? So T is much smaller than the evaporation time of the black hole. Okay, so we will find, actually so far we haven't even discussed the evaporation time of the black hole, but as a preview, and as I'm sure all of you know, the black hole itself tends to evaporate in a time scale which is very long, which we will calculate at the end of the next lecture. But this Penrose diagram then is not the correct Penrose diagram to use. And so we are not interested right now in time scales which are that long. So we are interested in some time scales that are much after the black hole, after the infalling matter has fallen in, and we're interested in time scales which are which are shorter than the evaporation time scale of the black hole. Okay, and this is an important thing to recognize. The second thing is that this region of interest. So I want to emphasize this is the horizon is here. Okay, the horizon is different from what we're calling the region of interest. The horizon, let me mark it here. Okay. The region of interest has the property that there's a lot of time in the region of interest. Okay, so it looks like a small part of the Penrose diagram, but there's actually a lot of time in this red region. And by that I mean that if you want to look at times between these two times, between this RH and between T-evap, where you see the laser pointer, there is actually a large time scale. For large black holes, these two times, the horizon radius and the evaporation time, are parametrically separated. In fact, they're parametrically separated by the entropy of the black hole, which is a very large number. And therefore, there is a lot of time where this metric that we wrote down, this generalization of the Schwarzschild metric, is valid. And this red blob, even though on the Penrose diagram it looks like a small region, is actually a region which basically involves most of the lifetime of the black hole. So it's not like we are exploring a very special part of the Penrose diagram or some very special part of the geometry. We are just ignoring the special parts of the geometry which in the Penrose diagram look big. We're ignoring the early part of the collapse, which is when all the matter and all the complications of what the initial matter were important. And we are going to some time which is where most of the black hole spends its life, which is a time when it's completely featureless and looks like this generalization of the d-dimensional Schwarzschild metric. Okay. Okay, so this is the first physical point that I'd like to make about the time scales that we're considering and the region of interest that we have. And this is important to remember whenever there is discussion of the information paradox. Whenever the people in LIGO or the people in the astrophysicists discuss black holes, they're not interested in this red blob, right? They're interested in, so our astrophysical friends are interested in parts here, right? And maybe in parts here when you cross the horizon. So this is where astrophysicists are interested in things. Right, they're interested in things where you have this infalling matter which is about to collapse, right? So not when it's actually collapsed, but when it's about to collapse. So they're interested in this part just before it collapses. We're interested in kind of, for theoretical reasons, in a different part of the black hole life, which is the part after the infalling matter has fallen away, and it looks like there's a smooth horizon, but actually, we are going to discover there are interesting quantum effects that are happening at the horizon. Okay, so this is where we are. So we are interested in red region, which is different from what astrophysicists are interested in. Okay, now let me say a few more things just to set notation. Once again, this might be something that many of you already know and are familiar with, but let me just set the notation. It's convenient to go to what are called tortoise coordinates. So tortoise coordinates are just a redefinition of the radial coordinate, which is done by defining a tortoise coordinate, which I denote by dr star, which is just dr by f of r. Okay. Now the question is, how does r star behave very far away when r is very large, and how does r star behave when r goes to rh? Okay. So near r goes to infinity, remember f of r goes to 1. Okay? And then that's because f of r was just what we wrote here. Okay? So remember, this is f of r. So let me just copy f of r. So as I said, we don't want the mass, but we have this f of r. Let me put it here. Okay? So near r goes to infinity, it's clear that f of r just goes to 1. And therefore, okay, it must be the case, there's an infinite amount of r of radial space near r goes to infinity. And therefore, it must be the case that as r goes to infinity, r star goes to infinity. Okay? So in flat space, it is indeed the case that as r goes to infinity, r star goes to infinity. In ADS, in fact, this will be different. If you're used to working with ADS black holes, you might be familiar with a different form of f of r star, where r star goes to a constant as r goes to infinity. But in flat space, r star also goes to infinity as r goes to infinity. Okay. Now the next question is, what happens as r goes to RH? Okay. Now as r goes to RH, f of r goes to 0, but it's important to analyze how it goes to zero. So it goes to zero it goes to zero exactly at the horizon. But if you're slightly away from the horizon, f of r is not exactly zero. And for a generic Schwarzschild black hole, which is the kind of black hole that we are looking at, f of r goes to twice k into r minus rh. Okay, so it's positive for r larger than rh, and it goes to twice k into r minus rh. And this number k, which is f prime of rh by 2, which you would just get by doing a series expansion, okay, this is what's called the surface gravity. And the surface gravity is going to keep appearing in whatever we do. But here we've just defined it as f prime rh by 2. There are other physical interpretations of the surface gravity that I'm sure you have encountered in your in your courses in GR. But for we can just define it right now as f prime rh by 2. And you see, if you do make that definition, that f of r near r goes to rh looks like twice k into r minus rh. Now, if you were to study what's called an extremal black hole, then for an extremal black hole, this would not be the correct expression, and the correct expression would have a quadratic variation near r equal to rh. But those are not the kinds of black holes we're going to look at. We're going to look at black holes which have a finite temperature, and when we do that, the surface gravity is something non-zero, and we have this linear variation near the horizon. Okay. So now what happens near r equal to rh? Okay. So near r equal to rh, if you look at this equation for dr star, it just becomes dr by twice k into r minus rh. Okay. And if you solve that equation, you will find that r star, okay, goes to 1 by twice k into log of r minus rh into twice k, okay, near r equal to rh. Now, this is not the exact form for r star. Okay, we didn't solve the exact form for r star, but what we need is the behavior of the tortoise coordinate near the horizon, and we've set this behavior to be 1 by twice kappa into 1 by twice k into log of r minus rh into twice k. In fact, you will notice that this constant that we've chosen here, there's some constant I chose here, and this is a choice. I could have chosen a different constant here, just by looking at the differential equation. I could have chosen a different constant. This choice is going to turn out to be convenient. There's nothing, sacrosanct about this choice. You could make a different choice, but it will just be convenient later when we go along and when we define various other coordinate systems. Okay. So in terms of r star, the metric reads the following. It looks like f of r into minus dt squared plus dr star squared, okay, plus r squared into d omega squared. Okay. So the metric kind of looks simple. Remember, there's an r here, and this is actually a function of r star when I write the metric this way. But when you write the metric in terms of r star, it's convenient to think of r, not always write r explicitly in terms of r star, but just think of r whenever you see r, just substitute it as being a function of r star. And f of r is whatever it is. It's some function which we gave in terms of r, which you can rewrite in terms of r star. And you see that the metric looks slightly simpler in terms of these r star coordinates. Okay, good. So far these are things which you're probably familiar with. Now, one more thing which I should remind all of you is that it looks like the horizon is a special place in this metric, because in this we are talking about the horizon, which is the part where f of r goes to 0. And you might have thought that and indeed people did think for a long time, till the work of Wheeler and others, that the horizon was some kind of singularity was some kind of a part where the metric became bad. But of course, now we know that that's not the case. And the way to see that is to go to what are called Kruskal coordinates, which we can define as follows. So once again, I'm just doing this just to set conventions and to make sure we're on the same page. Okay, and u and v, which are defined as this, and this k is our friend k, which we already encountered before, which was the surface gravity. Remember that this u is smaller than 0 outside the horizon. Okay, so as a convention, we've chosen this u to be smaller than 0 outside the horizon. Okay. Now notice that at the horizon, when we approach the horizon, we find that near the horizon, but maybe I should say a little bit well, okay, let me say a few more things before I go there. Let me just write the metric, and then I'll say a little bit more near the horizon. We have these are called, these u and v coordinates are called crucial coordinates, and in terms of these crucial coordinates, you see that du is just dt minus dr star into e to the kappa into r star minus t. Dv is dt plus dr star, okay, into e to the kappa r star plus t. Okay, and so in terms of these du and dv coordinates, we find that du dv is just dr star square minus dt squared into e to the 2k r star. Okay, now this term that you see here is something that should remind you of what we saw also in the metric. If you see this laser pointer, this is also the term that was that's the term that appeared in the metric, and there it was multiplied by some factor of f of r. Okay, but we already, by our definition of r star, we've already found that near the horizon, this factor e to the twice k r star is twice k r minus rh. Okay, here r goes to rh. Okay, and therefore we see that this factor that appears in the metric, which is f of r into dr star square minus dt squared, which looks like near r equal to rh twice kappa into r minus rh into dr star square minus dt squared, simply looks like du times dv. Okay, now there was a constant that appeared, and you see actually the virtue of the choice of constant that we made in defining this r star. So in terms of these coordinates, we see that the metric just looks like minus du dv plus r squared into d omega d minus 1 squared near r goes to rh. Okay, so there are other constants that people use in defining u and v. In terms of those other constants, you might get here where this laser pointer is different other constants in the metric, but in terms of constants that we have chosen, the metric really looks exactly like the metric of flat space near the horizon. Okay, okay, so the horizon in fact is at u equal to 0. Okay, the horizon is at u equal to 0, and you see that at the horizon, it is the case that you see the horizon is at u equal to 0, because that's the part where r star goes to minus infinity. But you see that at the horizon you also have that t, v remains finite at the horizon, and therefore t, which is proportional to log of v by u, goes to infinity. So this is the other behavior that's important to remember. Not only is it the case that r star goes to minus infinity near the horizon, the t coordinate goes to plus infinity near the horizon. Okay, so let's just draw once more the part that we are interested in, and let's forget about all the infalling matter and everything else that we had. So we have this horizon. Okay, this is future null infinity, this is the horizon, and this horizon has the property that r star goes to minus infinity and t goes to plus infinity at the horizon. Okay, so this is in some sense it's a convention. You could choose different kinds of conventions for r star, or you could choose different kinds of conventions for u, but this is the commonly adopted convention. And in terms of these Schwarzschild coordinates, it looks like the horizon is some point where something is going bad, but in fact it's just a point where your coordinates are going off to infinity. And in terms of these coordinate systems, it looks like there's a singularity in the metric. But if you go to these crucial coordinates, you see there's no singularity in the metric, and this region of interest is now somewhere here. Oops. Okay. So we're interested in some region of interest, which is here. Which is, as we discussed already, the region where t is large and r is close to rh. Okay. Now, behind the horizon, u becomes positive. So one can actually set up another copy of these Schwarzschild coordinates so that one can also write the region behind the horizon in terms of the Schwarzschild coordinates. And in terms of these new Schwarzschild coordinates, we again have, and this is something which is a convention which you should remember, it might sometimes be confusing, but we again have r star goes to minus infinity and t goes to plus infinity. Okay, so the fact that the horizon is r star goes to minus infinity and t goes to plus infinity is true on both sides of the horizon. Okay, it's true as you approach the horizon from outside, it's also true as you approach the horizon from inside. But there is something interesting that happens in these Schwarzschild coordinates as you cross the horizon, and that is that for r smaller than rh, okay, f of r changes sign. And that's clear because f of r was going to 0 smoothly near r goes to rh, and so for r smaller than rh, f of r changes sign. And therefore, okay, so for r smaller than rh, t is a space-like coordinate, and r star is the time coordinate. So when sometimes people say that space and time switch behind the horizon, this is what they mean. They mean that if you write the metric in terms of r and t, or in terms of r star and t, then it so happens that this coordinate that you were calling t ceases to measure what's time. It starts measuring something that's space, and that's it's clear because the sign of its coefficient in the metric changes, and time is now given by r star. Once again, I emphasize that's not because anything actually funny is happening at the horizon. In the uv coordinates, you could always have chosen t equal to v plus u and some x equal to v minus u, and t would always be a time-like coordinate. This capital T and this x would always be a spatial coordinate. And so the fact that there's a space-time interchange is not some physical property of the horizon. It's not that something physically is happening at the horizon or something fancy is happening at the horizon which is causing space and time to exchange. It's simply the fact that we're choosing a coordinate system in which the coordinate that we were calling the time coordinate now starts being a spatial coordinate, and the coordinate we're calling a spatial coordinate starts now being a time coordinate. Okay, so these are just conventions which I'm guessing that many of you are already familiar with, but I just wanted to review them to make sure that we're on the same page. So the next thing I want to do is now study the propagation of fields in this geometry. But before I do that, I wanted to ask if there are any questions about the geometry and aspects of the geometry that I just reviewed.
Yeah, there's actually a raised hand. Yeah, please go ahead.
Yeah. So my question to Suvrat is, for a asymptotic stationary observer, the horizon remains a special place, right?
For someone, the horizon is special in terms of only when you link it to Scri plus, and that the horizon is the pass boundary of Scri
Right.
plus. So it's not
Right.
that, yeah, but it's not it's not special in any local sense. It has some. If you look at the
Right.
global propagation,
Agreed.
then yes.
Yeah, agreed. But again, and there is no kind of globally defined uh, time-like killing vector inside the horizon, behind the horizon, right?
Correct. This r star is not actually, yeah, it's correct. It's not a killing vector. Yes.
So when you say that this is a time-like coordinate, you means that it can be any function of r star or r star t or something.
Yeah, sure. You could use r as something. Yeah, we are going to work often in these r star and t coordinates because when we study wave propagation, they're useful coordinates to use. We should just remember that r star is measures time, but yeah, you could use r star squared if you like.
And the fr that you are using here,
Yes.
that is generalizable for higher coordinate, higher dimension. Is it generalizable for lower dimension as well?
Yeah, you could study, well, you would have to study, if you went down to lower dimensions, you'd have to go to ADS, and then you could study like BTZ black holes in ADS 3, and then what we're saying would hold. But in flat space, 3 dimensions is not so interesting, and 2 dimensions I generally prefer not to think of. So there aren't so many lower dimensions to go to except for ADS 3. I mean, that's the context in which I like to think of things, but there are many higher dimensions to go to.
Okay.
Okay, thank you. Okay. Okay, so now the next thing we want to turn to is the propagation of fields in this geometry. Okay. So let's start by studying some massive scalar field, because that's a simple example to study. You can then generalize this to other kinds of setups and other kinds of fields. But this is the simplest example, and it in fact already captures all the essential things that we need to do. You could study the propagation of gravitons. It's just, if you'd like to spend some more time with indices and playing around with wave equations, it's possible to study the propagation of gravitons, propagation of gauge fields. But it's simplest for us to just study a scalar field, and a scalar field is just one. We'll study a minimally coupled scalar field, which obeys this kind of a wave equation. Of course, this field might have self interactions, might have other kinds of interactions. In fact, we will find that for the properties we are most interested in, these interactions are not even going to be so important. But for now, let's just consider a minimally coupled field, which is just, it's coupled to the background in this minimal way, so that this Laplacian is a Laplacian of the metric, of the background metric, but doesn't have any other couplings. So remember that this box is just 1 over square root minus g, square root minus g into d nu. Okay? And if we work out this Laplacian in tortoise coordinates, the square root of minus g is just f of r into r to the d minus 1 in tortoise coordinates. So, and that's because, from the dr star term, you get an f of r. From the dt squared term, you get an f of r. So you get an f of r squared. And you have an f of r squared. When you take the square root of that, you just get an f of r. And you have an r squared in front of all the sphere coordinates. There are d minus 1 of those. So you raise it to the power d minus 1, and taking the determinant, you take a square root, you get back r to the d minus 1. And it's also the case that g star star is minus gtt is 1 of f of r. Okay.
This determinant of G will also have factors from the spherical part, right?
Indeed, you're right. It'll also have factors from the spherical part, which I haven't written down. So you're right. Thank you. So the determinant of G will also have some factors that will come from the. Thank you. Let me write down. Which we're not going to be interested in at all. Thank you for pointing that out. Yeah, indeed. We are interested in the r star t coordinates. We will not be interested in these spherical things. In fact, they'll also cancel out in the equation, which I'll write down now, which will be correct. Thank you. Are there any other questions about this? Okay. So in these coordinates, the equation actually becomes the following. It becomes 1 by f of r into r to the d minus 1, which is just coming from the square root of minus g. As Sunil pointed out, there are these spherical terms, but remember, these spherical terms don't depend on r star or on t. And therefore, if you just look at the part which is the d star part, it doesn't care about what those spherical terms are. They cancel between the square root of g here and the square root of g in the denominator. And so we have d star into r to the d minus 1. The f of r, by the way, also cancels in the first term. There was an f of r in the square root of minus g, but remember the g star star has a 1 over f of r. So if you look at the first term, if you just take mu equal to r star, nu equal to r star, you don't actually get an f of r here. And then we have a minus 1 of f of r into a dt squared phi. Here everything cancels out except for this, the root minus g cancels out, and this f of r is just coming from the gtt term. Okay? And then we have a plus 1 over r squared into the Laplacian on the sphere acting on phi and minus m squared acting on phi. Okay? So there are, as Sunil pointed out, all these terms which come from the angular part, but all of those just go into the Laplacian, which acts on the sphere, which is acting on phi. Okay. Okay. So now, we can solve this systematically. It's possible to just separate the variables for this linear equation and solve this systematically. But in fact, we can take a shortcut to analyze the behavior of the solutions to this equation near the horizon. And the shortcut comes from looking at this equation and recognizing that in this equation, there are some terms that are going to become much more important than other terms near the horizon. And those are the terms that are multiplied with the 1 over f of r, which I'm now underlining with this laser pointer. And that's because near the horizon, we are going to have f of r goes to 0. And therefore, these terms are going to be important. And these terms are not going to be so important. And so near the horizon, f of r tends to 0. And so the equation becomes 1 over f of r, which is not important, but d star squared phi minus dt squared phi is equal to 0. Okay. And that's the only term that remains. Notice, I'm going to go back to the previous blackboard for a minute. There were some terms which had an r here. Okay. But when you differentiate these terms with respect to d star, you get a cancelling factor of f of r. So if you look at the terms which are most singular in f of r, it's when the d star goes and hits this d star and not this r to the d minus 1. And this r to the d minus 1 cancels off this r to the d minus 1. And this term, of course, is what it is. And these terms don't have a 1 over f of r at all. And therefore, if you're close to the horizon in these coordinates, the wave function simplifies greatly and it just becomes this very simple equation. Okay? I want to emphasize that this is independent. This is independent of many things. Okay, it's independent of the angular part. So, if you were to separate variables, in fact, in a little while we'll write down some expansion in terms of a sum over angular momenta, but it's independent of the angular part. Okay, it's independent of the mass. The mass has dropped out of this equation near the horizon. And if there are additional interactions, if the field had various interactions, if it had if there was a phi to the 4 interaction or other kinds of interactions, we see that those interactions are also not important in this near horizon behavior in these coordinates. Okay. So near the horizon, near r goes to RH, the wave equation takes a particular and very simple universal form. Okay. And so this is just some robust property of the wave equation near the horizon in these coordinates. Okay. So now let me go back to this original equation and write down a solution. Of course, as I said, there is an angular part of the solution, and there is, also there are other terms in the solution. But near the horizon, we find that phi simply goes to some integral of d omega into e to the minus I omega t into some function on the sphere, which we don't care what it is, plus some other term, some other function on the sphere into this, okay, and plus a Hermitian conjugate. And this is true as an operator relation. So if these a omegas and b omegas were some operator valued functions on the sphere, this would still be a valid expansion for the field. So these can be operator valued functions in the sphere. Okay. This expansion is only valid near the horizon, I emphasize. Okay, that's why we have an arrow here. This is only true near r goes to RH. It's not true away from the horizon. But we have a rather robust and simple result, which is that near the horizon, you have this very simple behavior, and it doesn't, the fact that the angular dependence or the mass, neither of those enter into the variation in the e to the I omega t coordinates and the e to the I omega r star coordinates. Of course, you can have an e to the minus I omega r star, and you can have an e to the I plus I omega r star. And there is, of course, a Hermitian conjugate, so I separated out the e to the minus I omega t terms and wrote down a Hermitian conjugate term. Okay.
So
are there any questions about it?
Yeah, there's a question in the chat asking if you can repeat the comment on r power d minus 1.
Oh, okay. Thank you. If you look at this, I guess the question was about why the r to the power d minus 1 cancels. If you look at this expression here, you'll get something which will have a dr by dr star. Okay? But dr by dr star is the term which is f of r. So you see that this dr by dr star is going to cancel this one of f of r. And the only term that is singular in f of r that diverges as f of r goes to 0 is the term where this d star goes and hits this d star and doesn't differentiate this. Okay, so that's why this r to the d minus 1 cancels off this r to the d minus 1 in the denominator, and that's why you get this very simple form for the wave equation, which is just d star square minus dt squared phi is equal to 0.
I have a question on this simple form. So none of the degrees of freedom in the angular part are entering this mode expansion.
We haven't written down the mode expansion yet. We will write it down in a minute. All I'm pointing out is that the variation in r star is linked to the variation in t independent of what the angular part is doing.
So the angular freedom is implicit in A and B.
Yeah, because these are operator valued functions on the sphere. So they're functions of this omega coordinate.
Okay.
I'm going to write down. I'll expand them in modes in a minute.
Yeah, there's actually a final question in the chat,
Good.
which
One
actually
more
I think
question,
is related to point C in this. But anyway.
Yeah, so if you have interaction terms like 5 to the 4, they also do not matter. You can see that actually from the wave equation. In the wave equation, so this mass is actually like a simple term. It comes from a phi squared interaction. You could have had like a V of phi here. You could have added like a V of phi here. But notice that the V of phi is also not going to have a term which is singular in this f of r. Okay? So if you go very close to the horizon, then this is basically all that remains. Okay, so in these coordinates, the solution close to the horizon is basically just universally fixed, regardless of whatever else you have away from the horizon. So it's not like the m squared or the mass of the field or the interactions are not important. They're just not important if you wanted to write down the near horizon behavior in these coordinates. So in these coordinates, the near horizon behavior is particularly simple. And you can see that, if you had a V of phi here, that V of phi would not appear here. There would be some V of phi here, but it would not be multiplied with the 1 over f of r. Okay. Okay, good. Excellent. So let's just, as Sunil was asking, we could, of course, I'm writing down these operator valued functions in the sphere, but that's not the most convenient thing to do. It is, in fact, most convenient to choose a basis for solutions, and that is by expanding out these operator valued functions on the sphere in terms of a basis of spherical harmonics. So I'm going to denote a spherical harmonic by YL omega. You will see this notation appearing again and again throughout the course, and that's because we are almost never going to be interested in the details of this YL omega. Okay? So this L here is actually a collective symbol for all the quantum numbers, for all the angular quantum numbers. Okay? So we will keep writing this L, but of course, even in 4 dimensions, you have a YLM, but we don't want to write down the YLM. So this L is just some symbol which tells us, think of a spherical harmonic in the sphere. Think of something that satisfies in the Laplacian, box omega on the sphere. On this YL is like L into L plus D minus 2 on YL. And so it's some eigenfunction of the sphere Laplacian. And there could be various other indices that are hidden inside it. There might be degeneracies in this eigenfunction, but we will never be interested in them. And so this notation you will keep seeing again. And this YL omega is just some basis of functions on the sphere. Okay. Then you can choose for this wave equation that I wrote, one solution. So there are, with this, one set of solutions which look like f in omega L r star into e to the minus I omega t YL omega. So I'm now trying to write down a basis of solutions. This was the basis for the angular part, okay, which we basically just introduced some notation. Now we're trying to write down something for the rest of the space-time. And we can choose 2 kinds of solutions. So we can choose one, and I'll explain what f in and f out mean. And we can choose another kind of solution, which looks like this. Okay. So this is a basis of solutions where this f in and f out have a certain specified behavior near r star goes to infinity. And the behavior is that f in as r goes to RH, okay, always from outside, is just, I'll explain what the notation is in a minute. And this f out as r goes to RH is e to the I omega r star plus g omega L into e to the minus I omega r star. Oh, by the way, I should have said there was a comment in the feedback we got which said that one wanted more details. So in fact, the place to find more details on this is a nice paper by Candelas, which is referred to in the review, and also a nice review, a very old review by Dewitt, in which these wave functions in flat space are analyzed in great detail. I think those are actually the best treatments of where you'll find more details about this wave function. And you will find the references if you just look at the review that we are using for the course. So these papers by Candelas and Dewitt, I'm actually also using almost the same notation, although not exactly. At points you'll see there's some factors of R and so on that are different in the notation, but if you work things out, you should be able to translate between the notation very simply. Okay. So the reason, the reason we call this first set of solutions F in is because, is by looking at how they behave near the horizon. So F in has the property that as t increases, r star must decrease. Now remember, r star decreasing actually means that you're going closer to the horizon, right? Remember, this is r star equals minus infinity, and we are approaching it from outside. So these f of in is something that's doing this. Okay, these are waves that are going into the horizon. Okay. On the other hand, these solutions which are f out are doing something else. Okay, the solutions which are f out okay, has the property that as t increases, okay, r star also increases, must decrease for constant phase. Okay, this is always, when I say must decrease, I mean to maintain the phase constant. And if I f out, as t increases, r star must increase for constant phase. Okay, and so this f r out has some waves which look like this. So these are some waves. I mean, they're coming out, but because they're coming out from r star goes to minus infinity, if you plot them, this is what f of out looks like. Okay? So you can think of f out as being waves of this kind, and f in as being waves of this kind. Maybe I should copy the expression so you can see once more what they are here and also in the presence of the diagram. Okay, let me also say a few words about these h omega l and g omega l's that I put in.
Yeah, so before that, I think somebody's asking what is f in and f out. I assume it's answered here now.
What is f in and f out? So f in and f out are two solutions that we chose. So I was looking for a basis of solutions here. I chose a basis for the angular part in terms of the spherical harmonics, and then I chose a basis for the rest of the spacetime as being a function of r star into e to the minus I omega t into yl of omega, and another one which is a different function of r star into e to the minus I omega t into yl of omega. This function of r star depends in general on L and on the mass and also on omega. But near the horizon, as we argued, both these functions f in and f out must basically go to e to the minus I omega r star. Okay? Now I have chosen a particular linear combination. I have chosen to write one solution which I'm calling f in, which has the property that it has an e to the minus I omega r star. So if you think of the entire solution, it looks like e to the minus I omega r star into e to the minus I omega t. This solution f out has an e to the plus I omega r star. It also has some component of e to the minus I omega r star, which I'll explain in a minute. But this component is what gives it the name f out, and this component makes it look like e to the I omega r star into e to the minus I omega t. Okay, so these are bases of solutions. I'm calling them f in and f out because this one is ingoing in the sense that I explained, in that when you go close to the horizon, as t increases, r star must decrease for phase to be constant, and that means the solution is moving inwards towards the horizon. This one actually has both components, but the important one we are interested in is this component, is the e to the I omega r star component. And this e to the I omega r star component has the property that as t increases, r star must decrease, and therefore it looks like it's outgoing at the horizon. Okay, and that's what gives it the names f in and f out. Okay. Okay,
Yeah.
let me say a little bit. Yeah, is there a question about this?
Yeah, I mean, not about this. I think it's just before this. There's asking if you're solving for the scalar propagator around the horizon or just the classical scalar equation.
We're just solving this classical scalar equation. We are not solving for the propagator. The propagator would be the 2-point function, which we are not solving. We're just solving the equation. So the equation we started with was this one. So we started with this equation, just to say. And we've been analyzing this equation. So everything I'm saying is about solutions to this equation. So I'm sorry, it looks like from the questions that I'm not being very clear. Let me stop here and pause for questions. Let me just recap what we've done so far. We're looking at the propagation of fields in the black hole geometry. We looked at a field which happened to be minimally coupled. Therefore, it satisfied this equation. Then I reminded you that in this equation, this Laplacian looks like 1 over square root minus g into d mu into g mu nu into square root minus g d nu. So it's some differential operator that has this expansion. Then we analyze what square root minus g was. It has this form. Okay, and we also analyze what this g mu nu was. That's because we have, you see g mu nu appears here. So that's the reason I wrote down this expression. Then we just expanded out this differential operator acting on phi. So this was an expansion for box of phi. Okay. And in this box of phi, I then pointed out that near the horizon, it so happens that f of r diverges. So you see two terms here which have an f of r, and these two terms are going to become most important near the horizon. There are other terms in this, but these terms are not going to be important. There might be a v of phi, an m squared phi, and so on. But these terms are not important near the horizon. And therefore, I said that near the horizon, the form of the equation becomes this. And the interesting part about the form of the equation is that the variation of phi in the r star t coordinates doesn't care about what phi is doing in the angular coordinates. It doesn't care about what it's doing with the mass. It doesn't even care about what interactions phi has. And therefore, in the limit that r goes to rh, you can expand phi in this form. In terms of some operator valued functions in the sphere. But of course, usually when we want to write down creation and annihilation operators, as we will want to write down, if you want to write down a basis of solutions, you also want to choose some basis for how things vary on the sphere. And therefore I said, we chose a basis of spherical harmonics for how things varied in the sphere. Also, we would like a solution everywhere in r star, not just a solution near r star goes to infinity. So I chose two solutions that had the right behavior near r star goes to minus infinity. And away from that, I've just given them some names. I've just said f in omega l r star, f out omega l r star. I haven't told you what they're doing as a function of r star. But if you wanted to know what they're doing as a function of r star, you could take this behavior near r star goes to minus infinity, near r goes to rh. You could plug it into the wave equation, and you would get a specification for how f in behaves everywhere out to r equal to infinity, and the same for f out. So I hope it's clear what we are doing. If there are any questions, more questions here, I'm happy to stop and we can discuss a little bit more if it's not clear what we are doing here.
Yeah,
I'm just trying to write down a basis of solutions for the Klein-Gordon equation.
Right. I think there's a general set of question about why does e power plus I omega r star not appear in f in from the chat.
It's a choice. You see, I have a choice of two solutions, right? And I'm going to explain actually why we chose these two solutions in a minute. But the reason, we could have e to the minus I omega r star, and we could choose e to the I omega r star, right? So I could have chosen, in principle, f. Maybe a more natural question. The question when I encountered this first was, I chose f in to be e to the minus I omega r star, and why did I write these factors h omega l and g omega l? I could have chosen, or somebody else could have chosen. In fact, the first time I saw it, I said, let's just choose e to the minus I omega r star near the horizon and e to the I omega r star. Let's just choose solutions which have this asymptotic behavior. Okay, so why do we write down these? Why do we write down one solution which looks like e to the minus I omega r star, multiply it with something we call h omega l, and write down another solution that looks like e to the plus I omega r star and multiply it with something that looks like g omega l? Okay, so it's a choice. We could choose any choice, and the natural question might be, why didn't we just choose these two solutions? The reason is that we need to make sure that the two solutions are orthogonal in the Klein-Gordon norm. Okay? And this depends. So, when you look for solutions which are orthogonal in the Klein-Gordon norm, these two solutions, if I call these, 1 and 2, are not orthogonal in the Klein-Gordon norm. Okay? In the Klein-Gordon norm. Okay? Whereas these two solutions, even though I haven't told you what they are, you could choose h omega l and g omega l so that these two solutions are orthogonal in the Klein-Gordon norm. Okay. Okay. Now the other part is that the reason we choose this g omega l, there are, if you just say the solutions are orthogonal in the Klein-Gordon norm, that's actually not enough to fix h omega l and g omega l. In general, we choose this g omega l so that at infinity, let me just say, so let me go to this picture here. We choose g omega l so that at infinity, so g omega l is chosen so that at infinity, sorry, maybe I'll write on a new page. So let me just write in a new page. It's chosen so that at r star goes to infinity, which is scribe plus, we have this f out goes to some other phase factor, which we can call t omega L, into some specified behavior into e to the I omega r star. So at infinity, once again, the behavior of the solution becomes simple, and you can solve this equation. And the reason you choose g omega L to be such that at infinity this solution becomes purely outgoing. Okay, it just has an e to the I omega r star term, and the e to the minus I omega r star term just dies off. Okay. Now, once you have done that, then there's one orthogonal combination, which is the one that we've chosen, which we've called Fe. Okay, so that's the reason for these factors of H omega L and G omega L. Okay? Let me say there's another way in which you can think of these F in and F out solutions, and that is to think of the geometry, not just the part that we're looking at, which is the horizon, but think of the geometry which includes the horizon. And if you have a massless field, to think of the geometry which has I plus. So F out specifies data here. And F in specifies data here. Okay, this is of course true for m squarely equal to 0. I mean, if you have a massive field, the massive field doesn't reach scribe plus. But one way to think about what F out means is that in the case when the field is massless, you think of the late time geometry, and you can specify data at the horizon, and you can specify data at scribe plus, and F out is what's specifying data at scribe plus, and F in is what is specifying data at the horizon. And the reason for that is that F out is oscillating very rapidly near the horizon. So if you were to think of some classical data, then the classical data is not, these outgoing solutions are not good to specify classical data at the horizon. And so one way to to specify F out is to specify something here, and the way F in is perfectly well behaved at the horizon, because it looks like e to the minus I omega r star plus t, and so F in you can think of as specifying data near the horizon. Okay. Are there any questions about this? So just to say once more what I wrote, F in as r goes to rh looks like e to the minus I omega into r star plus t. Okay, but remember that at the horizon, r star goes to minus infinity at horizon, but t goes to infinity in such a way so that r star plus t remains finite. Okay? And that's the reason this F in term remains finite at the horizon, because it has something that looks like e to the I omega r star plus t, whereas F out is some wave that is chosen so that it has very simple behavior at scribe plus, which is just e to the I omega r star, and e to the I omega r star minus t is something that's a good coordinate on scribe plus, and that's why you can think of F out as specifying data at scribe plus, and F in is specifying data at the horizon. Okay? But that being whatever it is, for us, we're just interested in how they behave near the horizon. And I just wanted to explain why, when we specify the data near the horizon, we introduce these coordinates, we introduce some constants, h and g, and we write down this slightly funny linear combination, which is not the simplest linear combination you could write down, which is e to the minus I omega r star and e to the I omega r star. And the determination is made by demanding how F out behaves near scribe plus, and demanding that these solutions be orthogonal in the Klein-Gordon norm. Okay. Okay. Are there any questions about this? If I was not clear, please stop, and I'm happy to answer questions.
Yeah. Did you claim that one of the two terms in F out dies near the horizon?
Did I say that one of the two terms in F out dies near the horizon? Yes, I would like F out to behave like e to the I omega r star near the horizon. Yes. Not near the horizon, near. Oh, did I say one term in F out dies near the horizon? Yes, yes. Sorry, you're not talking about scribe plus. You're talking the horizon. Yes, indeed.
Yes.
You see, because this term. So it's, you see, if you look at this term, okay, this e to the I omega r star term. Mm-hmm. So this term looks like e to the I omega r star minus t. Okay. So let's look at the other term, which is e to the I omega into r star minus t. As you come closer and closer to the horizon, this term starts oscillating more and more rapidly because r star goes to minus infinity and t goes to plus infinity. Okay, so this term oscillates very rapidly. This doesn't actually mean you can throw away the term near the horizon. Okay, it will be important for us that this term will contribute to 2-point functions. But if you wanted to specify classical initial data, if you wanted to specify an expectation value of phi near the horizon, then you would never use this very rapidly oscillating term to specify an expectation value for phi near the horizon. In the field expansion, you do need to keep this term, and this term is in fact the term that's more important for us because it's the term that will give us Hawking radiation. But what I wanted to say was, if you wanted, when I say data, I should say classical data. If you wanted to specify classical data, which means you wanted to specify some expectation value for phi, then you would not specify the expectation value for phi in terms of functions of this kind, which are oscillating very rapidly near the horizon. Okay. And does that answer the question?
Yeah, I did not understand. So, what was the aim here? I'm confused now.
What was the aim here? The aim here was just to write down two solutions of the Klein-Gordon equation, one of which has this behavior, the other has this behavior. Okay? So one has, and I was trying to explain why we introduced these factors H omega L and G omega L. In fact, you can check that these H omega L and G omega L are not entirely independent. We might have some assignment questions on that. They have to mod square up to 1, which is fixed by the canonical commutation relations. We're not doing something very complicated. It seems to me that there's some confusion, at least for some people who are listening. We are just taking the Klein-Gordon equation and we're just writing down the basis of solutions. We have written down two kinds of solutions. One solution which has this behavior near r goes to RH, and another solution which has this behavior. We have a second order differential equation. We have two solutions. I've written down the two solutions and I've chosen the basis. That's all I have done. I've not done anything beyond that. Okay, is this clear?
Okay, maybe I can take it up in the tutorial later.
Okay. So
just clarify, this is the basis of solutions for the full Klein-Gordon equation, right? Not just in the region of interest.
Correct. This f in, this f in is not going to behave like this e to the minus I omega r star when I go away from the region of interest. Right? It's going to have some complicated behavior which you have to solve, which you can solve on a computer. But this is the behavior near r goes to RH. So this f in is specified by its behavior near r goes to RH. As you go away from r goes to RH, you have to solve the equation. You will find some behavior.
Okay.
Okay, great.
Yeah, Suvrat, there are some more questions in the chat. You want to take them now or later?
Yeah.
Okay, one question is about what's the definition of orthogonality in the KG norm?
There's a Klein-Gordon norm. In that, there's a standard Klein-Gordon norm, and in that norm, these things are orthogonal. So if you open Biddle and Davis, for instance, you'll see a Klein-Gordon norm, these solutions are orthogonal in the Klein-Gordon norm. I mean, that's the condition for them to multiply independent oscillators when we do an expansion of the field. We want solutions which are orthogonal in the Klein-Gordon norm.
Then there's another question asking, does the f in solution continues to be purely ingoing at infinity?
Purely ingoing at infinity. No, so f in has some other behavior at infinity. F in is not going to behave just like e to the minus I omega r star at infinity. So f in will have some other behavior at r star goes to infinity. The point is that f in, so maybe one way to say it, this picture is that f out has some simple behavior at scribe plus, and f in has some simple behavior at the horizon. Okay, so that's one way to think about how what these solutions mean. It's also one intuitive way to think of why they are independent in the Klein-Gordon norm. Because if you think of the union of the horizon and scribe plus, that gives you like a Cauchy surface for the whole space-time, right? If you think of the space-time here, the space-time that we drew here, sorry, let me go back a few slides. Yeah. If you think of this space-time that you drew here, and you think of this union of where the laser pointers of union of the horizon and scribe plus, that's also a Cauchy slice, right? So if you had one set of solutions that give you nice data here and one set of solutions that give you nice data here, that's a good way of specifying data for the field on a Cauchy slice. So f out is specifying data on one part of the Cauchy slice, which is scribe plus, and f in is specifying data on another part of the Cauchy slice, which is the horizon. Okay? In fact, we are interested both in f out and f in near the horizon, But one intuitive way, if you thought of why these solutions should be orthogonal in the Klein-Gordon norm, is because they are specifying data on different parts of the of some Cauchy slice, which is a union of the horizon and sky plus. Okay. So, okay, but for us, if you're getting confused by this, just think of some solutions which are specified by this behavior near R goes to RH. Okay. And for some reason, which maybe because we would like to be perverse, we've chosen these some factors H omega L and G omega L. But the important thing is that we have F out, and F out has an e to the I omega R star with a factor of 1 in front, and then there's some other solution which is which has some H omega L and so on. In fact, these things are not going to be important in the derivation of Hawking radiation. Okay, so if you're getting confused by this, you don't even have to think so much about this. Just recognize that we have two solutions which are possible near the horizon, e to the minus I omega R star, e to the plus I omega R star. I chose one which was e to the I omega R star, and then for some reason which I explained, but it's not so important for Hawking radiation, we added these terms G omega L and H omega L. Okay.
Right. Actually, there are a couple of more questions.
Yeah.
Yeah. One is about, I think in this particular slide, why do you have a factor of R power 1 minus D by 2?
In this slide? That's because if you look at the behavior of the wave equation near infinity, one simple way to think of this is if you think of spherical waves in 4 dimensions, you have an e to the I k r by r, right? Spherical waves go like e to the I k r divided by r. They don't just go like e to the I k r. So that's why you have it, in d dimensions, the factor becomes r to the 1 minus d by 2. So that's the reason there's an r to the 1 minus d by 2. It would be wrong to say the wave just goes like e to the I omega r at large R. It doesn't go like that. It also has a certain die-off at large R, and that's the large R. That's the r to the 1 minus d by 2 here.
Right. Okay. There's another question asking, can the L-dependent part in the expression for F in be absorbed in the spherical harmonic YL omega? If then why are we writing H omega separately?
Oh, but the spherical harmonics you define once and for all, right? The spherical harmonics, I mean, this H omega L is like some term which is, it's in fact not even, it's not a pure phase, it's some order 1 term. The spherical harmonics are defined and normalized once and for all, right? If you open like Afkin or something, Afkin and Weber, there's some definition of the spherical harmonics. They're defined and normalized so that you have YL squared omega is equal to 1 on the sphere. So, H omega L is some other factor that's coming in addition to them. You can't absorb it in the spherical harmonic.
Right. Okay. And I think there's one final question, but you probably answered it many times. This is on the solutions of the Klein-Gordon equation, just e power IU and e power IV.
E to the IU and e to the IV.
Yeah, e power I capital U and e power I capital V. That's
no. Question. They're not e to the I capital U and e to the I capital V. These solutions, I mean, you could write down some other solutions that for a local region, they would look like that, but that's not a global solution to the Klein-Gordon equation. These solutions, in fact, near the horizon are looking like u to the I omega by k, in fact. So they're not looking like e to the I omega u at all. E to the I omega u would not be a solution. I mean, this is a black hole spacetime, so e to the I omega u and e to the I omega v are not solutions to the Klein-Gordon equation everywhere for all uv.
Right. Okay. I think you can go on now. Yeah.
Okay, great. So let me just write down a few things more. I'm going a little slower than I would like to. Okay, good. So, yeah, okay. So let's write down now an expansion of the field in terms of everything that we wrote. So we can write down expansion of the field. In fact, this is the reason we did all of this. And that expansion of the field now looks like this. Okay. Into F out. Plus B omega L into F in. Into YL omega plus Hermitian conjugate. Okay. So the reason we did all this song and dance was to get to this expansion of the field. Okay. Now here A omega L, B omega L, we have not normalized them in any way. Okay. They're not normalized. But you should think of them as these as annihilation operators. And that's why they multiply a factor of e to the minus I omega t. Okay, notice this e to the minus I omega t here. So there's an expansion of the field, and these are modes which reduce the energy that's conjugate to this time here. Okay, so these are modes which, if you act on a state with them, tend to reduce the energy of the state, and so they are like annihilation operators, and their Hermitian conjugates, which appear here. So there's an HC, which is actually important, are creation operators. Okay. So in the end, what we wanted to get to was this expansion of the field, which we have now written down. Okay. So this expansion of the field is like important. Okay. Okay. And these F out and F ins we discussed in great detail. There's some solutions of the Klein-Gordon equation. Okay. Now let me say one more thing. This is how the field looks like outside the horizon. But in fact, you could have asked, what happens as you cross the horizon? So far, I've been talking about these solutions of the Klein-Gordon equation, but you could have asked what happens as you cross the horizon. And that's because, remember, I have been saying so far that when you draw this horizon here, the region that we are interested in spans the horizon, right? And this is going to be very important for us because, we don't only want the expansion outside the horizon, we want the expansion also inside the horizon. Okay, so now what happens to the field, the quantum field inside the horizon? So inside the horizon, there's a similar expansion one can write down, and it looks as follows, and I'll write it down and then I'll explain why it is the case. Okay. I'm just writing down something and I'm going to explain in a second what I've written down. Excellent, F omega L. Excellent. Okay. So now behind the horizon, remember that now t is no longer the time coordinate. So I said we had these a omega L's that behave like annihilation operators, but now behind the horizon, the thing that should behave like an annihilation operator is the thing that multiplies not e to the minus I omega t, but the thing that multiplies e to the minus I omega r star. Okay? So behind the horizon, you can continue to solve the Klein-Gordon equation. Right? I said the field obeys the Klein-Gordon equation, but it obeys the Klein-Gordon equation outside the horizon. It also obeys the Klein-Gordon equation behind the horizon, right? Because the horizon locally, as we said, is not a special place. So this solution, F tilde, okay, is now a solution which has the property that as R goes to RH, from inside, it goes to e to the minus I omega r star. Okay. There is another solution which now goes like e to the plus I omega r star. Okay. But the solution that we want, which is the one which multiplies what we are calling annihilation operators, is a solution which multiplies e to the minus I omega r star. Okay. So we have a second solution of the Klein-Gordon equation, which is now multiplied by different operators, which gives us an expansion of the field behind the horizon, which is the solution that behaves like this. Now, it's very important that when we write down this solution, we do not go, okay, we never go deep inside the horizon. We do not go deep inside. So we are always in the regime where R minus RH by RH is smaller than 1. So we don't go like close to the horizon. And then if you go very close to, if you go close to the singularity, this would break down, this expansion would break down because curvature terms would become large, but we are never going to be there. We're always going to be just behind the horizon. And we also don't go behind the horizon in that we also stay in the regime where t is of the order of, we never go near t goes to 0. Okay. So if you start moving away from the horizon, remember this is t equals plus infinity. And then you could move here and, t would decrease. And eventually you would reach some point where t would be equal to 0 here. Okay, if you draw the eternal black hole diagram, t equal to 0 is the vertical line. But we don't want to explore that region because that's outside our region of interest. So we're just interested in expanding the field just behind the horizon. And just behind the horizon, we can write down another solution, another basis of solutions to the Klein-Gordon equation in terms of a different set of creation and annihilation operators, which I have now written down. Okay. Now, there is one last thing I should say, which is there are two different operators which have appeared here, which are these A tilde omega L and the C omega L operators. Now, you see, there was also some expansion I had for the field outside the horizon. Right? That expansion I had for the field was this expansion. Okay. Now, remember, I said to you that e to the I omega into r star plus t is perfectly well behaved at the horizon. So you see that there is a term here which looks like e to the minus I omega into r star plus t. You see, if you combine these two terms, you'll find some term which looks like e to the I omega into r star plus t, right? So you see, it must be the case that by continuity of the field, the fact that the field is continuous across the horizon, you can equate the terms, the oscillators that multiply e to the minus I omega into t plus r star outside the horizon and e to the minus I omega t plus r star inside the horizon. So by a requirement of continuity, we find that these C omega L modes have an expression which is A omega L into this H omega L factor I mentioned plus B omega L into this G omega L factor that we had previously. Okay. On the other hand, the A tilde omega, which appears here, you see there's another expression here, which is an A tilde omega. This is the term which is multiplying a term which looks like I omega t minus r star. Okay? And that's not something that's regular. So there was this term which was sitting inside f out, what we were calling f out outside the horizon, which was also multiplying in something which looked like e to the minus I, omega into r star minus t. But A tilde omega is not related to the oscillator that multiplies f out. So A tilde omega is not the same as A omega L. So I emphasize once more, we had an expansion previously which had an A omega L, but this A omega L is different from this A tilde omega L. It's some different operator, which is not related to the old A and B operators by continuity. And that's because e to the I omega t minus r star is not continuous across the horizon. Okay? So A tilde omega L are new modes. And in fact, at some point in the later parts of the course, when we do ADS-CFT, we will spend some time in trying to understand how we should understand this A tilde omega L. But the fact that these A tilde omega L exist and you do need these new degrees of freedom behind the horizon is something that's just fixed from the fact that you want to expand the Klein-Gordon equation behind the horizon. You need modes which go, which have e to the I t plus r star and e to the I t minus r star. And therefore, you need, apart from one set of modes which just cross the horizon by continuity, which are these C omega L modes, you just are forced to add, just to get a set of solutions to the Klein-Gordon equation, some new modes behind the horizon, which are the modes that we have written down here. Okay. Okay. Actually, I did a little less than what I wanted to do, but this may be a good time to stop because tomorrow we can then relate these modes to these near horizon modes that we discussed and derive the form of Hawking radiation. But before that, maybe I could spend a few minutes addressing questions if there are questions about this expansion that we had. Just to emphasize, let me just try and recap what I said, and then I can take questions. We said that we had an expansion of the field. We had a field which obeyed the Klein-Gordon equation. You can expand this. We are interested in how this field behaves in this part which is across the horizon, which is called the region of interest. If you're outside the horizon, we had this expansion in terms of these mode functions f in and f out. And we said, the expansion looks like some operators A omega L plus some, which multiply some function that we call f out, plus some operators B omega L, which multiply some function that we call f in. Then we said, when you go behind the horizon, the field continues to obey the Klein-Gordon equation, because the fact that it obeys the Klein-Gordon equation is just a local property of the geometry. It doesn't care about whether you're on one side of the horizon or the other side of the horizon. The horizon is just some coordinate artifact for us. And therefore, there must be a similar expansion of the field behind the horizon. But when we do this expansion of the field in terms of these r star t coordinates, we find one thing that is unusual. The thing that's unusual is that now, because r star is the time coordinate, what we are calling, or what we will need to call, the annihilation operators are things that should multiply e to the minus I omega r star. And that's why, we now combine all the annihilation operators into some function that multiplies, that looks like e to the minus I omega r star near the horizon, and then does whatever else it does as you go deeper inside the horizon, which you can obtain by solving the Klein-Gordon equation. And then we said, well, by continuity, we have these two solutions, one of which look like e to the it plus r star, one of which look like e to the it minus r star. The terms that look like t plus r star have to be continuous across the horizon, outside and inside the horizon. And that led us to this relation that c omega l, this c omega l, was related to what we were calling a omega l and b omega l by continuity. On the other hand, this a tilde omega l is just some new set of operators which now appear, but which are required in the expansion of the field, just to get a complete set of solutions to the Klein-Gordon equation. Okay, so that's a good place, I think, to stop for today. Let me just give you a brief preview of what we would like to do tomorrow. What we'd like to do tomorrow is, we've written down now this expansion of the field, which comes from solving the wave equation in this background. What we'd like to do tomorrow is now do play this game that we played in the first two lectures of defining these near horizon modes near the horizon. When we do that, we will find that these a tilde omega l modes and these a omega l modes that we wrote in the previous slide become thermally occupied, just because these near horizon modes have to be thermally occupied. So, we will find that when you define these near horizon modes from this expansion of the field that's written here get related to these global modes which are appearing in the global expansion of the field. So this expansion we've written down as a global expansion, but the near horizon modes are going to get related to these modes that we have on this slide. And then the fact that the near horizon modes are thermally occupied will immediately tell us that these global modes are thermally occupied, which we'll see tomorrow. So we'll find now, we've done all the work, and tomorrow we just need to, play the game that we played in the first two lectures, and it will immediately drop out that we will find that, the black hole emits radiation with a thermal spectrum. So let me stop here for questions, and since I'm sure there's some questions, and we can continue tomorrow.